You know that satisfying whoosh of air you get, like when you're pumping up a basketball? Or maybe think about the raw power of an air wrench just blasting through a bolt. Compressed air, it's everywhere. We use it constantly. But have you ever, actually stopped to think about the tech behind that whoosh? It's pretty wild when you get down to it.
It is fascinating, isn't it? That
Mm.
everyday experience, it relies on some seriously clever engineering principles.
Yeah,
And, it's really amazing just how much air compressors and blowers impact, well, almost everything. Industries, even our everyday lives, it's all connected to them in some way.
for sure. And that's exactly what we're going to explore today, right here on the deep dive.
Yeah.
You know, you've provided some really awesome, really informative materials on this, and we're going to use those as our guide to really get into the world of air compressors and blowers. Basically, what we want to do is break down how these things work, what makes them different from each other, and why they're so incredibly important across such a huge range of applications.
Yeah, it's a really comprehensive collection of resources you put together, and we'll definitely be referencing those throughout our conversation. So we're going to be unpacking the core science behind air compression, the different types of compressors and blowers out there, the key components that make them tick, how they actually operate step by step, potential issues that can crop up, and yeah, we can't forget about that often overlooked but totally essential part, the air receiver.
Exactly. We want to go beyond just the surface level, get into the real nuts and bolts of the mechanics and engineering behind all of this. But don't worry, we'll keep it fun and avoid getting too bogged down in super technical jargon. Okay, so let's start right at the beginning. What exactly is an air compressor, like at its most basic level?
At its core, an air compressor. It's a device that takes energy, usually from an electric motor, but it could be diesel or even gasoline, and it converts that energy into potential energy. And that potential energy is stored as pressurized air. The way it does this is by essentially squeezing or forcing a certain volume of air into a much smaller space.
Yeah.
So as the volume shrinks, the air molecules get packed closer and closer together, and that's what causes the pressure to really shoot up.
So it's like taking a big deep breath and then forcing all that air into, I don't know, a tiny box or
Yeah.
something, right? Makes it more powerful.
Exactly. That's a perfect analogy. And that high pressure air, well, it becomes a reservoir of stored energy, right? You can think of it like winding up a spring. You're putting energy in, and it's just waiting to be released to do work. And with compressed air, that stored potential energy can be unleashed as kinetic energy to power all sorts of things, from pneumatic tools to inflating tires, you name it. All kinds of industrial processes, too. Now, a fundamental category of air compressors that we should explore first is the positive displacement compressor.
Positive displacement. That sounds pretty intense. What's the basic idea behind that?
Picture this. You take a specific amount of air, like a set volume, and you trap it in a chamber. Then you shrink that chamber, you physically reduce its size. That's positive displacement in a nutshell. So by mechanically decreasing the volume while keeping the amount of air the same, you force the pressure to go up. It's unavoidable.
Gotcha. So it's a very direct mechanical way of squeezing the air into a smaller space. And from the materials you shared, it looks like there are a few common types of these positive displacement compressors, right?
You got it. The most common types are reciprocating piston compressors, which, as the name implies, use a piston that moves back and forth inside a cylinder. This motion is what compresses the air in a sort of, cyclical way. Then we have rotary screw compressors and rotary vane compressors. These guys both use rotating components to compress the air more continuously. And actually, rotary screw compressors were highlighted in your sources as often replacing piston compressors, particularly in high-demand, high-output applications. Maybe we should spend a bit more time on those.
Yeah, let's do that. What makes rotary screw compressors so well suited for those kinds of heavy-duty jobs?
Well, the cool thing about rotary screw compressors is how they achieve compression. They use these two helical rotors, think of them like screw-shaped parts, that mesh together inside a casing called a stator. So as these rotors spin, they draw air in at one end, and then as that trapped air travels along the spinning screws, the space between the rotors and the casing steadily gets smaller and smaller.
Hmm.
This constant reduction in volume forces the air to compress, creating a nice, steady stream of high-pressure air at the output.
So instead of that back and forth piston motion, it's more of a constant squeezing action, right? Sounds like it would be much smoother.
Exactly. This rotary motion results in a much smoother, less pulsating flow of high-pressure air compared to the more intermittent output of a piston compressor.
Hmm.
And because of that smoother operation, Their ability to handle those large volumes of air efficiently at high pressures and generally lower vibration, they've become the go-to choice for all sorts of industrial applications, things like powering manufacturing equipment or running those heavy-duty air tools you see on construction sites.
Makes sense. Now, so far we've been talking mostly about compressors, but one of the documents you shared was titled Air Compressors and Blowers. Clearly, they both involve moving air and increasing pressure to some extent. So what's the real difference between them?
That's a great question, and it's definitely important to make that distinction. The key difference lies in how much they can increase the pressure of the air. Specifically, we're talking about the pressure they can create above normal atmospheric pressure. Blowers, they're designed to move large quantities of air, but they do it with a relatively small increase in pressure, typically up to about 1 bar, which is roughly 14.5 pounds per square inch above atmospheric pressure. They're more about moving a large volume of air from point A to point B. You can think of them as high-volume air movers rather than high-pressure generators. Okay, so blowers are high-volume, low-pressure increase. What are some of the ways we use them? Your sources actually had some really good examples. Blowers are often used with air diffusers, for instance, like in wastewater treatment plants where they aerate sewage. Think about turbochargers and superchargers in cars, too. They force more air into the engine to boost power. Even a simple electric fan, the kind you use for ventilation in a room, it's working on the same principle, moving a large volume of air at low pressure. The key takeaway here is that blowers are usually rotary devices that are built for maximizing airflow, but only with a modest increase in pressure.
Oh, okay. So it's like the difference between a gentle breeze from a fan and the concentrated blast of air you get from, say, a tire inflator. So where do compressors fit on that pressure spectrum?
Compressors, they're all about generating much higher pressures. The documents you gave me indicate that compressors generally operate in a pressure range starting around 7 bar, about 100 psi, and can go much higher. And we'll discuss this a bit later, but multi-stage compressors, those can reach some pretty impressive pressures, up to 70 bar in some cases. That's over 1,000 psi.
Wow, that's a huge difference. So the internal design of a compressor must be much stronger to handle that kind of force, right?
Oh, absolutely. Blowers are almost always rotary devices, optimized for high flow and low pressure differences. Compressors, though, they can be either reciprocating, that's the piston-based type, or the rotary screw type we talked about earlier. They're usually designed to handle less airflow compared to blowers, but they're built tough with the strength and precision needed to handle those big pressure differences. And often, to deal with all the heat generated during compression and to make the whole process more efficient, compressors will have things like intercooling and aftercooling systems built in. We'll talk more about those later.
Let's talk about that heat for a second. One of the sources you provided had a section on single-stage compressors, and it seemed like the heat generated is a major factor.
It's definitely something to consider. So in a single-stage compressor, all the compression happens in one step, all inside that one cylinder. And as you might imagine, that creates a lot of heat, kind of like what goes on inside a diesel engine. And this high temperature, well, it can cause some issues and potential safety concerns.
Like what? What are the main downsides of that intense heat buildup in a single-stage compressor?
One of the big concerns is that the temperature can get high enough to actually ignite any oil vapor that's mixed in with the compressed air. And obviously that's a fire hazard. But it's also a waste of energy, right? Because all that heat isn't really contributing to compressing the air to the pressure we want. It's basically an unwanted byproduct that we want to minimize for both safety and efficiency reasons.
That sounds pretty serious. Okay, let's switch gears a bit and get into some of the science behind air compression. Your sources mention that air acts like a near-perfect gas, and it follows these, well, gas laws during compression. Can you break those down for us?
Of course. The main idea here is that air, which is mostly oxygen, about 21%, and nitrogen, about 77%, with some other trace gases mixed in, it behaves very much like what we call an ideal or perfect gas under normal conditions. And this means we can use some basic gas laws like Boyle's law and Charles's law to predict how it'll act.
Okay, and just to refresh our memories, what do these laws tell us about compressing air?
So Boyle's law says that if you keep the temperature of a gas constant, the pressure and volume have an inverse relationship. Basically, if you squeeze a certain amount of air into half its original volume, the pressure doubles. Charles's law, on the other hand, says that if you keep the pressure constant, the volume of a gas is directly proportional to its absolute temperature. So if you heat up a gas but keep the pressure the same, it'll expand. Now, these two laws are often combined into a more general equation called the combined gas law. And it can be written in a few ways, like PV MRT or PVT is constant. In this equation, P is pressure, V is volume, M is the mass of the gas, R is a gas constant, and T is the absolute temperature.
Got it. So as we compress the air, what happens to these variables like pressure and temperature according to these laws?
So when we force the air into a smaller volume, that means V is decreasing. And the mass of the air, that's Gishi, it stays the same because we're not adding or removing air from the system. So what happens? Both the pressure, P, and the temperature, T, they increase. And understanding these relationships is super important for engineers when they're designing air compressors, to make sure they run efficiently and safely in all kinds of conditions.
Now, I noticed one of the sources had these diagrams, an ideal PV diagram and an actual PV diagram. I'm guessing PV stands for pressure volume, right? What do these diagrams tell us about the compression cycle?
You got it. PV diagrams are basically graphs that show how the pressure and volume of the air inside a reciprocating compressor cylinder change during one complete cycle of operation. The ideal PV diagram, that gives us a simplified theoretical view of this cycle broken down into 4 stages. So the line from point 4 to point 1, that's the air intake, where fresh air is drawn into the cylinder as the piston moves down. Then from point 1 to point 2, that's the compression stroke. The piston moves up, the volume of the trapped air decreases, and the pressure skyrockets.
Wow.
From point 2 to point 3, that's the air delivery. This is where the compressed air is pushed out of the cylinder through the discharge valve. And finally, the line from point 3 back to point 4, that represents the expansion of any air that's left over in what we call the clearance volume. The clearance volume is that tiny bit of space that remains above the piston when it's at the very top of its stroke.
Okay, and I saw some specific terms defined there, like clearance volume, swept volume, induced volume. Could you clarify those?
Sure. So the clearance volume, we'll call it VC. That's the smallest volume left in the cylinder when the piston is at the very top of its stroke, what we call top dead center. The swept volume, or V's, is the volume that the piston actually pushes through as it moves from the bottom to the top of its stroke. It's simply the difference between the total volume at the bottom of the stroke, V1, and the clearance volume, VC. And then we have the induced volume, V, which is the actual volume of fresh air drawn into the cylinder during the suction stroke, which is that 4-1 part of the cycle we talked about.
And there are a couple more terms, volumetric efficiency and compression ratio. How do those fit into this PV diagram picture?
Volumetric efficiency is a really important measure of how well a compressor is performing. It's the ratio of the induced volume, V, remember that's the actual amount of fresh air drawn in, to the swept volume, V, which is the theoretical maximum the cylinder could take in based on the piston's movement. So it tells us how well the compressor is filling its cylinder with fresh air during each cycle. Then we have the compression ratio. This is the ratio of the volume at the beginning of the compression stroke, V1, to the volume at the end of the compression stroke, V2, which is basically the clearance volume, VC. And it's interesting because for an ideal gas, this compression ratio is also directly related to the ratio of the discharge pressure, P2, to the intake pressure, P1.
Okay, so that gives us a good idea of the idealized compression cycle. But you mentioned the actual PV diagram, and it definitely looked, well, less perfect. Those lines were kind of wavy instead of nice and straight. What's causing those deviations from the ideal?
Yeah, those wiggles in the actual PV diagram, they represent the real-world imperfections and all the dynamic stuff that's not captured in that simplified model. For instance, the way air is drawn in induction and pushed out delivery, represented by lines 4-1 and 2-3, those are heavily influenced by the suction and discharge valves. So the way those valves open and close, their tendency to bounce a little, the inertia they have, the force from their springs, even little fluctuations in back pressure in the discharge line, all those things contribute to those non-ideal curves on the actual diagram.
So those little bumps and wobbles are basically the compressor breathing in a less than perfect way, right? Because of the physical limitations of those moving parts.
Exactly. Now, let's talk about the different types of compression processes that can happen. Isothermal, adiabatic or isentropic, and polytropic. These terms, they describe how heat is exchanged or not exchanged with the surroundings as the air is compressed.
Okay, sounds like thermodynamics 101. What are the key differences between these types of compression?
Isothermal compression, represented by the equation PV equals C, where C is a constant, it's the most efficient, at least in theory. In this process, the temperature of the air stays constant the whole time. That would mean that every bit of heat generated during compression is removed instantly. And since no energy is wasted on heating the air, isothermal compression requires the least amount of power to get a certain pressure increase. But achieving perfect isothermal compression in a real compressor is extremely difficult, practically impossible, really.
So it's the ideal, but not very realistic. What about adiabatic or isentropic compression, where PV raised to the power of 1.4 equals C?
That's the other extreme. With adiabatic or isentropic, there's absolutely zero heat exchange between the air and the environment. All the work done by the compressor goes into raising the air's internal energy, which means the temperature goes up a lot. This type of compression requires the most power compared to the others, and it's less efficient overall because so much energy is spent just heating the air. True adiabatic compression would only happen in a perfectly insulated compressor running super fast, so fast that there's no time for heat to escape.
And then there's polytropic compression, PV raised to the power of, well, something between 1 and 1.4 equals C. Where does that fit in?
Polytropic compression is the reality. It's what happens in pretty much every air compressor out there. It's somewhere between isothermal and adiabatic. So some heat is allowed to escape during compression, but not enough to keep the temperature completely constant like an isothermal. That exponent in the equation, which is usually between 1 and 1.4, and often around 1.3 as your source pointed out, it tells us how much heat transfer is happening. Because some heat escapes, the temperature doesn't rise as much as an adiabatic, and as a result, the compressor doesn't have to work as hard to reach a certain pressure. So it's the compromise that engineers aim for in real-world compressor designs.
Makes sense. It's the real-world scenario where some heat escapes, making it more efficient than adiabatic, but not as efficient as the ideal isothermal. Now, going back to the heat issue with single-stage compressors, the sources really stressed the importance of using multi-stage compression, especially when you need high pressures. Why is it so much better to compress the air in stages instead of doing it all at once?
That heat generated during single-stage compression, that's the main reason we need multi-stage compression. Remember, the heat causes an extra pressure increase on top of what the piston is doing mechanically. But that extra pressure from the heat, it's only temporary. When the air cools, you lose that pressure gain. So you're using more energy for a pressure boost that doesn't even stick around.
So you're basically working harder for no real gain in the end.
Exactly.
Yeah.
And while isothermal compression in a single stage would solve that problem, it's not practical. So the solution, the clever engineering solution, is to split the compression into multiple stages. Then you cool the air down between each stage using intercoolers. This multi-stage approach with intercooling, it gets the whole process much closer to that ideal isothermal condition, making it more efficient and reducing the final temperature of the air.
It's like taking a bunch of small sips of compression with a cool down break in between instead of one big hot gulp, right? So what are the specific advantages of this multi-stage compression, especially with that interstage cooling?
Several advantages, actually. First, like we mentioned, single-stage compressors struggle with efficiency when they have to handle high-pressure ratios. But if you divide the compression into multiple stages, the pressure ratio in each individual stage is much lower, and that helps maintain a high overall efficiency. Second, single-stage compression can result in ridiculously high air temperatures at the output, and that can lead to a whole bunch of problems. We're talking excessive carbon deposits from the oil, added stress on the parts, lubrication breakdown, even a higher risk of explosions. So multi-staging with intercooling, that brings those temperatures down significantly, making it safer and more reliable.
Those sound like some pretty serious issues that multi-staging helps prevent. Are there any other benefits?
Definitely. Multi-stage compression also uses less total power to compress the air to the final pressure. The interstage cooling, it cools the air down, which makes it denser before it goes into the next stage. So compressing a smaller volume of cooler air takes less work. How many stages you need depends on the final pressure you want to achieve. Plus, by spreading the compression over multiple stages, you get a more even temperature rise in each stage, and that helps protect those critical components like the valves and springs from damage. And actually, your source pointed out that if you look at the PV diagrams for single-stage and multi-stage compression, the area enclosed by the multi-stage cycle is smaller, which represents the work saved by going with multi-stage and intercooling.
Okay, so the extra complexity of building a multi-stage compressor is definitely worth it for the performance and safety benefits. The sources also briefly mentioned some perks of having a lower compression ratio in each stage. What are those?
Right. Lower compression ratios per stage lead to some good things. Mainly, it means lower air temperatures at the output of each stage. And like we said, that helps reduce those nasty carbon deposits, extends the life of the valves, and reduces leakage past the piston rings and valves. And those intercoolers are crucial here too, removing heat between stages, which leads to lower temperatures and less work overall.
So, to sum it up, multi-staging with intercooling gives us less work needed for compression, higher efficiency, more compressor capacity, a closer approximation to that ideal isothermal compression, smaller components because the delivered air is cooler and denser, lower and safer air temperatures overall, better moisture separation, and even the possibility of using a smaller air receiver. That's a lot of advantages.
It is quite a list. Okay,
Okay,
let's shift from the theory to the actual hardware. Your sources gave a good overview of all the key components. Where should we start?
let's start at the beginning with the air filter. It seems simple enough, but the documents really stressed its importance.
It's absolutely critical. The air filter, usually made of things like felt, paper, metal gauze, or nylon mesh, it's the first line of defense for the whole system. Its job is to keep dirt, dust, and other junk from getting into the compressor with the intake air. This is important for preventing wear on those internal parts, like the piston rings and valves, and it also helps prevent buildup on the valves, which, remember, can be a fire hazard.
So, a dirty air filter can do more than just reduce performance. It can actually be dangerous.
You got it. A clogged air filter can cause the intake pressure to drop, meaning the compressor has to work harder to pull in air. That increases the compression ratio and bumps up the discharge air temperature. And when the temperature goes up, you get more carbon deposits forming, which can lead to overheating. In extreme cases, if that temperature gets too high, it can even reach the point where the oil in the system ignites. That's a fire or even an explosion waiting to happen. Your source mentioned some heavy-duty filters are made of copper or steel mesh with a paper element inside and a wire mesh outside, just for extra durability and filtration.
Okay, so regular air filter maintenance is crucial. Got it. What's next in line? The cylinder liner, right?
Yep, the cylinder liner is the inner surface of the cylinder where the piston slides back and forth. It's usually made of a special kind of cast iron that's super tough and wear resistant, and it's usually surrounded by a cooling jacket where water or another coolant flows to absorb all that heat from compression. The cylinder liner is machined to be extremely smooth, so the piston rings can seal properly against it, preventing leaks and ensuring efficient compression.
And then we have the suction and delivery valves. Seems like they play a pretty important role in managing the airflow.
They're essential. These valves, which are often multi-plate designs made of stainless steel, they control the flow of air into and out of each stage of compression, and they ultimately direct the pressurized air to the air receiver, or wherever it needs to go. The design, how they're made, and how well they work are all crucial for the whole compressor system to operate smoothly and reliably.
The sources mentioned something about low inertia automatic valves that operate based on tiny pressure differences. Can you explain that in simpler terms?
Sure, these valves are engineered to open and close super fast in response to even the slightest pressure changes created by the piston moving back and forth. Low inertia means they have very little resistance to changes in motion, so they react almost instantly to those tiny pressure differences. This ensures that air flows in during the intake stroke and out during the discharge stroke, with no delays or backflow. The materials they're made of, things like hardened and polished steel for the valve seat, hardened nickel or stainless steel for the valve plate, and a special kind of hardened steel for the spring, those are all carefully chosen for their durability and their ability to handle those high-speed impacts and the corrosive environment inside the compressor.
And it sounds like even small problems with these valves can lead to big issues for the compressor.
Absolutely. Even though the suction and delivery valves might look similar in the same compressor, the spring tension and how much they're allowed to open, which we call the valve lift, those are carefully adjusted and can be different depending on their job and the stage of compression. If a valve opens too much, it can slam into its guard and wear out prematurely. And if it's slow to close or closes too late, that messes up the compressor's efficiency, meaning it delivers less air. And we've already talked about how those carbon deposits can cause problems too, making them leak or stick, which can lead to overheating and all sorts of other issues.
Okay, so moving on, let's talk about the piston. What are the important design features and materials they use for the piston?
So for compressors that don't use oil lubrication in the cylinder, what we call non-lubricating types, they often use pistons made of lightweight aluminum alloys. But compressors that do use oil in the cylinder, they usually use pistons made of a special type of cast iron, and those have piston rings. The piston rings do two main things. They create a tight seal between the piston and the cylinder liner so the compressed air can't leak past. And in lubricated compressors, they help spread a thin layer of oil on the cylinder walls and scrape off any excess oil so it doesn't get into the compression chamber.
And the shape of the piston can vary depending on the type of compressor, right?
Right. In single-acting compressors, where the compression only happens on one side of the piston, They often use what's called a trunk-type piston. But for more compact multi-stage compressors, they might use a tandem piston, which is basically multiple piston sections connected together. Aluminum alloys are often preferred for those non-lubricated compressors because they're wear-resistant, strong, but lightweight, which reduces stress on the parts, and they don't expand as much when they heat up, which helps maintain those precise clearances inside the cylinder. In lubricated compressors, the piston rings are usually made of a type of cast iron, and they're often thicker or has special coatings in the higher pressure stages where they have to handle more force and heat.
So we've got the piston moving up and down. What connects it to the rotating parts that power everything? I'm guessing that's the piston rod and the connecting rod.
You got it. In larger, high-capacity reciprocating compressors, the piston is attached to a strong piston rod, which is usually made of a high-strength alloy steel to handle all the force. And to prevent leaks where the piston rod goes through the cylinder wall, they use special seals and packing rings. The connecting rod, often made of forged alloy steel, which gives it great strength while keeping it lightweight. That's the crucial link between the piston rod moving up and down and the crankshaft rotating. It basically converts that linear motion into rotational motion.
And all those moving parts are supported by bearings. What kind of bearings are used in an air compressor and what makes them important?
Modern high-performance compressors often use thin shell bearings. These are designed to work with higher oil pressure, typically above 2 bar, to maintain a film of oil that prevents metal-to-metal contact. The more traditional thick shell bearings can handle lower oil pressure and sometimes even operate safely down to around 1 bar. The bearings that connect the connecting rod to the crankshaft, those are called big end bearings, and the bearings that support the crankshaft itself, those are the main bearings. These are often made of copper-lead alloys, which are strong, can handle wear particles, and last a long time as long as they're properly lubricated.
And at the heart of it all is the crankshaft, the part that everything connects to and transmits the power. What are the key features of the crankshaft's design and construction?
The crankshaft, in an air compressor, it's usually a single strong piece, and it often has these built-in counterweights. Those counterweights are super important for balancing the crankshaft as it spins at high speed, which helps reduce vibrations and stress. The material of choice for most crankshafts is forged carbon steel, known for its strength, its ability to handle those repeated stresses, and its resistance to fatigue. You generally won't find cast steel crankshafts in high-performance compressors because they're not as strong. The surfaces of the crank pins where the connecting rods attach and the journal pins where the main bearings support the crankshaft, those are ground and polished to very precise tolerances to ensure smooth operation and long bearing life.
And all these moving parts, they're housed within the main structure of the compressor, right? The frame and the crankcase.
Correct. The frame and the crankcase are the backbone of the compressor. They're typically made of sturdy cast iron, often with a box-like shape for strength and rigidity. The bore that holds the main bearings in the crankcase that's machined with extreme precision to make sure the crankshaft is perfectly aligned. Any misalignment there can cause vibrations, wear out the bearings faster, and potentially even damage the compressor.
We've talked a lot about heat, and we know that multi-stage compressors use intercoolers. So what exactly are these intercoolers and how do they make things more efficient?
Intercoolers are basically specialized heat exchangers that are positioned between the compression stages. Their job is to cool the air down after it's been compressed in one stage before it goes into the next stage to be compressed further. And that cooling is really important because it makes the air denser, which improves the efficiency of the next stage and reduces the total amount of work the compressor has to do to reach the final pressure.
And are there different types of intercoolers?
Yeah, there are 2 main types you'll see, multitubular and single coil. Multitubular intercoolers have a bunch of copper tubes arranged in a bundle, and those tubes are expanded into brass plates at each end. They're designed to allow for expansion and contraction as the temperature changes. The whole bundle is housed inside a cast iron casing that has safety features like a bursting disc, which protects against overpressure, and a drain pocket to collect condensation. If one of those copper tubes springs a leak, you can usually plug it or replace it. Single-coil intercoolers, as the name suggests, use one long coiled copper tube inside a protective casing, and they usually have a bursting disc too. If a single-coil one leaks, you usually have to replace the whole coil. Aftercoolers, those are similar, but they're located after the final stage to cool the fully compressed air before it goes into the air receiver.
It seems like moisture is a constant concern in all this. You mentioned drain traps earlier. What do they do?
Drain traps are super important. They automatically remove water and oil that condenses out of the compressed air as it cools down, both after each stage of compression and in the air receiver. Getting that moisture out is crucial, especially after each stage. If water builds up, it can wash away the oil that's lubricating the cylinder walls, which causes more friction and wear. Plus, water can corrode the internal parts and break down the oil itself. So regular inspection and maintenance of those drain traps is really important to make sure they're doing their job.
Now, starting a big air compressor must put a huge load on the motor. That's where the unloader comes in, right?
Exactly. The unloader prevents the compressor from having to start up against a full load of compressed air. There are a few different ways to do this, like restricting the intake air, adjusting the compressor speed, though that's not as common for starting, or bypassing the discharge air back to the intake. But the most common methods, especially for large compressors like those used on ships, involve holding the suction valves open during startup. This basically stops any serious compression from happening until the motor is up to speed.
So it's like starting a car in neutral, letting the engine get going before you put it in gear.
Perfect analogy. One common type is a suction valve depression unloader, which is often fitted to each stage in large compressors. It's usually controlled by a solenoid valve or by air pressure. Your source even described a two-stage unloader that uses little balls, springs, a diaphragm, and control air pressure to hold those suction valves open. The goal is to significantly reduce the load on the motor during startup so it doesn't draw too much current and potentially get damaged.
Okay, we've covered the air intake, the compression stages, and the cooling system. Now, what about lubrication? That's the oil pump's job, right?
Right. The oil pump circulates oil under pressure to all the bearings and other moving parts to reduce friction, wear, and heat. It's usually driven by the crankshaft, either with a chain or gears. The oil pressure is carefully controlled by an adjustable screw on the pump, and there's an oil filter at the inlet to keep the oil clean. Some compressors, especially water-cooled ones, might also have a water pump attached that's driven by the crankshaft. Others rely on an external water supply. And of course, the whole system is powered by a motor, which is usually electric and connected to the crankshaft with a flexible coupling and often a flywheel to smooth out the rotation.
Now, besides all these main components, we also have various valves and safety features. Let's talk about those in more detail. We touched on the suction and delivery valves earlier, but the sources went into more specifics about their different types and how they work.
Right. As we discussed, those are self-actuated valves, meaning their opening and closing are controlled by pressure differences. In smaller, high-speed compressors, they often use reed valves, which are simple and react very quickly. Basically, they're thin strips of steel that are clamped at one end and cover or uncover ports as they bend in response to pressure changes. For medium-sized and large piston compressors, ring valves or plate valves are the standard, and sometimes you might see poppet valves, which are kind of like the valves in a car engine.
And those ring and plate valves have a pretty complex design, right? All to make sure they seal well and last a long time.
They do. Ring valves typically have a seat with these concentric circular slots machined into it, and those slots are sealed by individual rings made of a durable, non-metallic material. These rings are held against the seat by springs, and their lift is controlled by